Hello, all. Welcome. Our speaker is going to be Larissa Montas, a PhD candidate in the Civil Architecture and Environmental Engineering department. She is going to talk about a 3D-Fate and transport model that explains measured changes in PAH concentrations from weathered oil. So Larissa is a Go MRI scholar with a beach exposure and child health study, and she's actually a UM alumni with undergraduate degrees in civil and environmental engineering and a master's degree in civil engineering with environmental focus. So thank you very much, Larissa. I won't take too much time talking about all the awesome things that you've done because you're going to talk about them very shortly. Larissa.
Thank you, Dr. Pranoy. I will share my screen now. Can everyone see my screen?
Yes.
Yes.
Something's not working here.
Yeah, we saw the Florida and Louisiana map slide.
Okay. Are you able to see the title screen?
No.
The easiest thing to do would be to okay, yeah, perfect.
Okay, I'm sorry about that. We practiced earlier, but there you go. So thank you, Dr. Pranoy, and good morning to all. I'm Larissa Montas, an environmental engineering PhD student at the University of Miami. And first and foremost, I would like to thank the CAE department for the opportunity to share with all of you part of my research and for organizing this event. I would also like to thank the Gulf of Mexico Research Initiative for funding part of my studies, and the Civil Architectural and Environmental Engineering Department for providing research and teaching assistantships to its students. The work that I'm about to present is part of the Beach Exposure and Child Health Study, BEACHES, which is a joint project between 3 universities, the University of Miami, North Carolina A&T, and the University of Texas School of Public Health. And this study integrates oceanographic data to forecast health risks from oil spills. This is an overview of my presentation. So in the next minutes or so, I aim to go over the background for my study, the study location, and discuss oil spills and human health, and do a very brief overview of oil chemistry, because chemistry is behind everything that I do. And then I would like to discuss how we measure concentrations for oil spill chemicals in the environment versus how a model may estimate a concentration. And finally, go over one of the studies for my thesis, which is how a 3D fit and transport model can assist in explaining measured changes in PAH concentrations from weathered oil. But before I start, I'd just like to talk a little bit about oil and oil projections in the coming years. I was talking to a student and she was asking me, an undergraduate student, she asked a really good question. She was asking, well, what is the relevance of your study? How can we use your study moving forward in the future? Because, you know, we never want another major oil spill to happen. Well, We all know of the shift in global trend to move to electric vehicles and sustainable energy sources and so forth. But even if we move to a total, let's say total vehicles move to electrical energy, oil will still be used in the future. These are oil predictions for the year 2040, and they take into account moves towards sustainable energy sources. And as you see, oil is here at the top, leading in energy production, and that is because it is behind the energy production for our electrical grid. And also, very briefly, if you're working as an environmental engineering PhD student, if you're interested in fate and transport processes in coastal areas, then this is a project that also might be of interest to you. So our study area is located in the northern Gulf of Mexico. And this study was motivated by the outcome from the oil spill that followed the explosion of the Deepwater Horizon oil drilling platform back in April 2010. And there was a loss of human life for those who worked at the platform. A massive oil spill occurred for 87 days that reached the coastlines of 5 different states. And the oil that made landfall impacted shorelines, including recreational beaches. And one example of a beach that was impacted by oil is Pensacola Beach in Florida. So this is a photo of Pensacola Beach after it was impacted by oil. And you will notice that the beachgoers, people are enjoying the beach in the vicinity of the stranded oil. And after the oil spill ended, the oil was cleaned up and was no longer visible. However, some layers of oil remained buried underneath the sand or in nearshore waters. And depending on the erosion of the coastline or the occurrence of storms, it may have gotten re-exposed. Satellite images capture the extent of the ocean surface oil slicks at the time of DWH. And this particular image corresponds to May 24th. And the oil slicks are shown as the white sheen located here. And the inset at the bottom left-hand corner shows the location of the oil slick with respect to the northern Gulf of Mexico. So back in 2010, when the oil spill was going, there was a lack of information on the health risks posed by the oil spill. And uncertainty in the general population and risk perceptions varied. So you had people, like the beachgoers at Pensacola Beach, going to the beach despite the presence of the oil, whereas other people, avoided the beaches, avoided all the beaches. And people who lived in the Gulf Coast wanted to know the amount of the more toxic oil spill chemicals that they had potentially been exposed to. However, the methods for determining the concentrations of oil spill chemicals in environmental media, which represent human exposure zones, were resource intensive, and the information was made available to the public several days after potential exposure had occurred. So basically what I'm saying is people had to go out there, take environmental samples, take it back to a lab, measure it, and then tell the public, these are the chemicals that were present in the oil that made landfall. This resulted in closure of beaches, tourists avoiding the areas, and huge economic impacts to the Gulf Coast, including Florida. So in our study, we proposed that we need to use science-based information to make public health decisions. So for example, to advise the general population on the risks associated with oil spills and avoid adverse risk perceptions when they are unfounded. Now, I would like to talk a little bit about oil spill chemicals, a topic which I find fascinating. Oil spill chemicals represent a risk to the environment and human health. And oil, crude oil, petroleum, raw oil, whatever you want to call it, it's a fascinating substance. It's one of the most complex and diverse organic mixtures found in nature. It contains thousands of different compounds, with the main ones being hydrocarbons. And all these chemicals, thousands of chemicals, are allocated to 4 major groups depending on their molecular structure. So for example, alkanes, which are straight chain hydrocarbons, which you can see at the top of the slide, cycloalkanes, which are cyclic, aromatic hydrocarbons, asphaltenes or asphaltics. And also oil contains metals, sometimes up to 0.2% or 1% metal content may be present. So for the aromatic hydrocarbons, they have one or multiple rings and are a particular health concern due to their genotoxic, mutagenic, and carcinogenic properties. So they may make you sick. And one particular group of aromatic hydrocarbons that is found in crude oil is BTEX, which is benzene, toluene, ethylbenzene, and xylene. And the chemicals in this group are classified as volatile organic compounds. So because they're volatile, inhalation would be the primary route of exposure. And the other major aromatic compounds of concern are the polycyclic aromatic hydrocarbons, which you see here. And these chemicals have the potential to be taken up by multiple exposure routes. And that would be ingestion if you eat seafood, or inhalation when they're volatilized, and absorption. They may be taken up through the skin, through contact. So the simplest form of a PAH is naphthalene, which is composed of 2 aromatic rings, followed by phenythrin and anthracene, which have 3 rings. And I'm going to talk a little bit later on about alkylated PAHs. So an alkylated PAH is a PAH that has one of the hydrogen atoms has been substituted by a methyl group, as you can see, for example, for alkylated phenythrin here, which has 1 methyl group, or C2 phenythrin, which has 2 methyl groups. Normally, crude oil or petroleum is enriched in alkylated PAHs just because of the way that the crude oil was formed. And in the past, traditionally, when crude oil was analyzed, only parent PAHs were measured. So a parent PAH is the PAH without any methyl group substitutions. And the oil that was released during DWH was enriched in parent PAHs. So once again, we're out of all the hundreds and thousands of chemicals in crude oil, our study focuses on PAHs because of their genotoxic, mutagenic, and carcinogenic properties. So as engineers, particularly those engineers that are focused on producing work that might be used as input for health risk estimates, we think it's important to estimate the concentrations for the more toxic oil spill chemicals, such as PAHs that impact coastal areas, such as Pensacola Beach that you saw. But this is a really complex task because the weathered oil that makes landfall has a really different overall chemical composition than the crude oil which was released. And this is because once the oil is released in the marine environment, processes such as evaporation, dispersion, dissolution in ocean water, photooxidation by the sun, and emulsification, which is promoted by wave action, oil and water emulsification, or water and oil emulsification. These chemical and physical properties transform the chemical composition of the oil. And these processes are collectively called weathering, and they are dependent on the time that the oil is in the environment. And it is important to know that weathering affects concentrations for PAHs in different ways because PAHs have widely variable physical chemical properties. So just very briefly, naphthalene, which is the most simple of the PAHs with 2 aromatic rings, has a really high solubility in water, whereas benzo-GHI-pyrene, which is a heavy PAH with 5 aromatic rings, has a really low solubility in water. Can you see my mouse as I move it and I move it along the slide? Can someone let me know?
Yes, we can.
Okay, thank you so much. Alternatively, we're also looking at boiling point, which is related to vapor pressure and ties into the rate at which chemical will evaporate into the atmosphere. And we also see that A chemical such as naphthalene, once again, has a really high boiling point or low vapor pressure, which means that it has a tendency to evaporate more rapidly than, let's say, once again, benzo-GHI perylene, which has a really high boiling point. So moving forward, we're focusing on, in this study, we're focusing on the changes in oil spill chemical concentrations. And we know that we know the chemical composition of the oil that originally was released, because that oil can be sampled, can be taken to a laboratory, and the concentrations for each chemical can be measured using laboratory analytical techniques. Likewise, we can take samples of weathered oil at the ocean surface, and we can also take samples of weathered oil in different environmental matrices, such as sediment. We can also sample for oil spill chemicals in air, and I will speak a little bit more about this later on. So, for example, this slide just shows you, oil as it might have been sampled from Pensacola Beach in Florida. It's taken to the lab, and then the result might be a concentration of, let's say, 2.3 micrograms per kilogram for C1 naphthalene, which has one methyl group. So how do we do this, and why analytical techniques for measuring chemicals is important? We measure chemicals normally in the these type of organic chemicals in the lab using GCMS, or gas chromatography mass spectrometry, and sometimes selective ionization monitoring is used as well. I'm just going to spend 30 seconds going over this technique, because this is what informs us on the concentration of the chemical that was present in that environmental sample. But this analysis sometimes has several limitations. It doesn't normally provide results up to 100% accuracy. And that is because of the detection issues inherent to the method. So, for example, this is a TIC, a total ion chromatograph produced after GCMS, and it's the different peaks here show the relative concentration of all these PAHs, that are listed here, and time the x-axis is time, and this is just related to the retention time, or the time that the chemical was present in the process before it was detected, before it peaked. And as you can see here, phenythrin and anthracene have the same atomic mass unit, because phenythrin is an isomer of anthracene. It has three aromatic rings with no substitution. So what this means is that for this type of technique, you have a resolution issue, since these two chemicals have similar atomic mass units, and thus very similar physical chemical properties. So going on to one of the studies in my PAH, the goal of this study was to explore the potential for integrating PAH, or specific chemical prediction capabilities, into a well-established oceanographic model. And our overall goal was to expand current modeling capacity to predict concentration distributions for individual toxic oil spill chemicals as a starting point for human health risk estimate. And we hypothesized that pH concentration changes in the oil pre-landfall were related to each chemical's physical chemical characteristics and weathering period from its age at sea. That is the time it was present in the environment after release. And that this could be predicted by an oil fit and transport model. So this is a really busy slide. I would like you to focus here first on this map and the concentration gradient. This is the output of the oil connectivity modeling system. This is an oil fit and a 3D oil fit and transport model that was developed by Dr. Claire Paris from Rasmus here at the University of Miami. And this oil spill fit and transport model has the capacity to predict where the oil will go, the mass of oil, and the total concentration of chemicals that are present in the oil expressed as total petroleum hydrocarbons. Basically a bulk measurement that just tells us the amount of hydrocarbons in total that are present in the oil. This model provides really valuable information because it models oil as individual Lagrangian particles in a 3D grid. And due to time constraints, I won't talk more about the model, but it's a fascinating model. As environmental engineers, we can do a lot with this model if you're looking at the fate and transport processes of contaminants in the ocean. But for now, I will focus on the capacity of this model to model crude oil as Lagrangian oil particles, and use a small time step, which is 2 hours, to predict the location of oil particles. So I use the output of this model in conjunction with environmental engineering sampling data. So let's say weathered oil that was sampled all along the Gulf of Mexico, or oil that was stranded in beaches along the Gulf of Mexico. And this next map represents locations where oil was sampled by the EPA. So samples of oil were collected, date stamped, and then taken to a laboratory for analysis, as I mentioned earlier. So as part of my study, I integrated both data sets. I took the model's output for the Deepwater Horizon oil spill and the environmental engineering sampling data set collected by the EPA with information on the chemical concentrations for hundreds of PAHs during DWH. I conducted spatial analysis in Python on both data sets to determine which modeled oil particles coincided with environmental samples. And the coincidence was determined on spatial coincidence, that they occupied the same space. In this case, spatial coincidence was determined by a 50 kilometer by 50 kilometer grid, and also in time, where an environmental sample for weathered oil was present at the same time as the model predicted an oil particle would be there. Then I calculated percent depletion for a range of individual chemicals, where percent depletion was calculated as the concentration of the PAH in the raw oil at time 0 minus the concentration of the PAH in a particular weathered oil sample divided by the original concentration. And then the time for time 0 and age at sea are determined by the model, as estimated by the model. And these are part of my results. So what you're seeing here, you're seeing concentration, percent depletion as calculated by the prior equation, and age at sea at the bottom. And this informs on how depleted each chemical was in the environment. So we're using a real measurement, a chemical measurement measured in a laboratory, but for our time axis, this time has been provided by the model. So for example, naphthalene, which is a really simple PAH with 2 aromatic rings, at 92 days at sea, we can see that we can't see naphthalene over here. It was 100% depleted. However, C4-naphthalene, which is a naphthalene molecule that has 4 methyl groups, by 92 days at sea, we can still see it was only 94% depleted. And this trend is similar for 94 days at sea or 98 days at sea, where naphthalene is 100% depleted, but the alkylated naphthalenes are less depleted. And then depletion increases with alkylation. So C1 naphthalene, which only has 1 methyl group, is highly depleted between 99 and 100% depleted, whereas C4 naphthalene, which has 4 methyl groups, is not so depleted. And then just checking my time, okay. If we look at results for another PAH, let's say phenythrin, we see that for phenythrin, depletion is less than for naphthalene for similar time periods. The similarities between the two chemicals is that the parent PAH phenythrin is highly depleted at 92 days at sea and over 100 days at sea, whereas the other alkylated phenanthrins are not as depleted. And something interesting to note here is that because this graph was generated using analytical measurements, the concentrations for phenythrin are listed as phenythrin anthracines, because this is a limitation that we have in the lab, as I showed you in the slide earlier, where it's very difficult to differentiate between the concentrations of phenythrin and anthracines due to the fact that they are isomers. So their total concentration is listed here. And for example, as I said before, phenythrin, the parent, is 100% depleted, whereas C4 phenythrin anthracene, which is depicted by the gray circle, is shows less depletion. So how do we explain these results? What is driving this mechanism what is driving the mechanism of high depletion for a parent PAH and low depletion for the alkylated PAHs? I will answer that question in a short while. I would also like to show you, lastly, the graph for crisines. And for crisines, we see a dissimilar pattern, where we see that the percent depletion for crisine has no pattern. We have 0% depletion all the way up to 100% depletion for 92 days at sea. And that somehow doesn't make any sense. You would expect high percent depletion for crisine. The reason behind these results is that crisine has many isomers. And when an environmental sample for crisine is measured in a laboratory, all these isomers interfere in the analysis, and it's hard to differentiate between the crisine that came from the oil and the crisine that is ubiquitous in the environment. So now to answer that question on why we have such different depletion rates for a parent PAH, such as phenythrin and naphthalene, and their alkylated PAHs. And the reason is that they have widely variable vapor pressures. As you can see, naphthalene has a vapor pressure at 25 degrees Celsius of 11.3 pascals, whereas this molecule here that has 4 methyl groups, 2,3,6,7 tetramethylnaphthalene, has a vapor pressure of 0.1 pascals at 25 degrees Celsius. And that plays into the rate of evaporation for each of these molecules in the rate of evaporation of each of these molecules in the environment. And similarly for phenythrin, we see that between phenythrin, the parent PAH, and phenythrin with 4 methyl groups, there is a really large gap in difference in vapor pressure. And that explains the differences in percent depletion. This next slide shows the relationship between the degree of alkylation, or the number of alkyl groups that a PAH may have in oil, and vapor pressure. So we see that vapor pressure decreases sharply with an increase in alkylation. This is naphthalene, the parent PAH, and here at the bottom is tetramethylnaphthalene, which has 4 methyl groups, and its vapor pressure is almost close to 0. So we know that chemical will have does not have a tendency to evaporate as much as naphthalene, which is a parent PAH. Before I move on to the conclusion for this study, I would like to speak for 2 minutes on the continuation of the work that I'm doing. So when oil is released in the environment, many chemical transformations and processes are happening at the same time. Oil is being dissolved in ocean water, oil is evaporating, and weathered oil is impacting shorelines. Something that I've learned through my studies is that the impacts of oil on coastal areas and possible impacts to human health have very different timescales. For example, weathered oil might beach in 2, 3, or 4 days after it is released in the environment. However, as soon as oil slicks begin to form in the surface of the water, that oil is evaporating, along with all these hundreds and thousands of chemicals that are also present in oil. And I find this fascinating because as these chemicals evaporate at different time frames, depending on their particular vapor pressure, and as they evaporate in the atmosphere, they start reacting between themselves. And they create new chemicals. So for example, this slide shows you cumulative oiling for DWH for the 87 days of oiling that occurred in the Gulf of Mexico. And this arrow here shows wind direction. And these black arrows are intended to depict the evaporation of the fresh oils, volatile organic compounds, intermediate organic compounds, and compounds with low volatility. They're all released in the atmosphere. They're all undergoing chemical reactions between each other, and they are generating compounds with lower vapor pressure. So these gases, oil is liquid, chemicals evaporate, they become a gas. These gases react between themselves. They create new compounds with lower vapor pressure. These new compounds condense, they form particles or aerosols, and these aerosols are transported to the coastal environment all in a matter of hours. And this leads me to my last slide, which is part of a different study that I'm also working on, and it's to look at the air quality impacts of the DWH oil spill. This little arrow at the bottom shows the location of the DWH site. And these are 3 locations along the Gulf Coast: Venice in Louisiana, Gulfport, Mississippi, and Dauphin Island in Alabama. And I generated bivariate polar concentration plots using a Python code for the air quality data for air measurements. As I said earlier, we need to monitor oil spill chemicals not only in water, in sediment, and in weathered oil, but we also need to monitor the air to determine the comprehensive impact from oil spills. So with the air monitoring data, air that was collected in canisters and taken to a laboratory with these measurements for 87 days of the oil spill, I generated this bivariate polar concentration plots. And these plots are really easy to interpret. This axis represents wind direction. So 0 is true north, wind true north, and 180 degrees is south. And it represents the direction that the wind was blowing into the site that collected the air canister for the measured chemicals in the air. And we see that for Venice, Louisiana, the concentration of naphthalene is really high, coming in from the direction of the DWH oil spill. So once again, this is Venice, Louisiana. This is its relative direction. And this is the plot that corresponds to naphthalene for the air samples collected at Venice in Louisiana. And we can see that the highest concentrations, which correspond to 0.48 micrograms per meters cubed, were detected from air blowing in from the DWH site. And then the concentration gradient decreases, and this dark color represents really low concentrations. It is interesting that no measurements of naphthalene were detected from the air coming in from the continental shelf. So my conclusion is that these naphthalene concentrations are related to the naphthalene that evaporated from the ocean surface oil. With that, I would like to move to the conclusion for the study that I just went over. We conclude that it is possible to extend existing oil spill forecast models, such as the oil CMS developed by Dr. Claire Powers at Rasmus, so to estimate concentrations for individual PAHs. In order to do so, we need to disaggregate oil into individual chemicals, and we also need to integrate each chemical's physical-chemical properties. And further research is needed to address the totality of the environmental impacts from oil spills by assessing not only measured oil spill concentrations in weathered oil, ocean water, and sand, but also in air monitoring measurements. And with that, I would like to open the floor for questions.